In this lecture, we will discuss the notion of a stochastic process. As we've been discussing before, we can have stochastic variables that has realization with more than one outcome. So the event from the sample space omega will turn into a 1 or 2 or 3-dimensional stochastic variable. Of course, that could be an n-dimensional stochastic variable as a stochastic vector, as we discussed before, making this a realization in an n-dimensional space. If we let n, the dimensionality, grow to infinity, then we have a stochastic process, meaning that each realization in itself is a function starting at minus infinity going on to plus infinity. Obviously, from a practical point of view, you will not have any measurement that starts at minus infinity and plus infinity. You will have something starting at time, say, 0, and ending up at time n or n minus 1, so that you have n samples. And in this sense, it would be, there's really no difference between a stochastic vector and a stochastic process from a practical point of view. Of course, in theory, this is a difference, but we don't have to differentiate too much on the notion of the stochastic vector and stochastic process here. Just as for the stochastic variables, a stochastic process can be a discrete time event or a continuous time event, so that you have things that occur on a continuous time or a discrete time. I will typically draw them as functions like this, even though they might be discrete functions. So you typically, for each realization, you will have a different function outcome, different function outcome. So you will have infinitely many realizations, infinitely many functions that are feasible, that can occur from the stochastic process. And this ensemble of different realizations is what constitutes the stochastic process. From a practical point of view, of course, we only have a realization in the sense that we are observing a set of samples and we claim that these are a realization from a stochastic process. And then we try to impose the structure, the statistical properties of the stochastic process onto the realization we see. And whether that is a good or a bad model depends on the data and on the assumptions we can make on the process as such. As before, the mean of a process is something that then is the mean value at a given time of the process, where you average over all possible realizations. So this is the mean of the process at time t over all possible realizations. The variance is similarly the variability on the time point t1. The covariance between x1 and x2, that means how much do the stochastic variables at time t1 and t2 depend on each other in this process. Clearly, we don't have to have time on the axis here. We could, for instance, say, for instance, we're looking at a sonar case. That means that we will have spatial sensors and time measuring time as well. So then, in this case, the stochastic process will be two-dimensional. So where we have time and space on the different axes. There can be many other parameters as well. And later on, we will extend the notion of a stochastic process to a multi-dimensional stochastic process, basically just adding indices. So there's much more difference to it. But what is relevant then is speaking about the correlation, the dependencies between the realizations at different times, say different spaces. So are there dependency from this point to this point, or from this point to this point, and so forth? These are the things we try to model when we look at realization and claim this to be a realization of a stochastic process. We try to create these dependencies from what the data we have observed, and therefore try to model the observation and get these statistical structures describing how the different samples at different time, space, and so forth points depend on each other. Clearly, we cannot estimate, for instance, the mean or the variance of a stochastic process at a given time if we only have a single realization. So in some sense, we need to form averages over the measurements we have observed, and therefore infer something about the mean or the other properties or moments of the stochastic process. And to be able to do that, we have to make assumptions on the process that we are observing. And the first assumption here, the assumption we will make in this course, is that the processes are wide-sense stationary, or weakly sense stationary. This is also called. That means that we have to fulfill three properties. First of all, the mean function has to be constant and finite, meaning that the mean value at each time point of the process is the same. In that sense, you can, of course, then average the different realizations that you have and get an estimate of the mean as such. So you don't have to average the mean at a given time over all possible realizations of the process, because of course you don't have that. You can only get a single estimate in that. Secondly, the autocovariance function will only depend on the time difference of t minus s. That means that the dependency of the process, the realization here I'm drawing, of course, but then the process is the same if I am at different points, but they are equally far apart from each other. This is a very strong assumption, of course not something that will hold in reality for most forms of data, but it's something we can say that it's approximately true, or locally true. During this interval, it's a reasonable assumption and so forth. This is typically what we call locally stationary. So we say that the data we are observing seems to have this particular property over a limited time interval. So we assume that the data is locally stationary. We also assume that the variance is finite, which is of course not a problem for anything that is a real measurement. We will also assume that all processes are ergodic. But basically, this only means that it is possible to estimate, for instance, the mean from the realization. If a process is not ergodic, it is not possible to estimate the mean from realization. You have to have the ensemble of all possible processes to be able to estimate it. So from a practical point of view, that of course would make that a very bad model. So in our case, we will always assume that the models are ergodic. So let's consider an example. So if I have a function that is a sinusoid, which has a stochastic variable as amplitude and a stochastic phase, and those two are independent of each other. Then x of t here will be a stochastic process that occurs from all time, from minus infinity to plus infinity, even though that the amplitudes and the phase parameters are, of course, only a single variable, so that each time you draw the stochastic process, you will get a different outcome. So you would get one which looks like this, that would be a sinusoid. Then you would get another one with the same frequency, but of course then another phase and amplitude. So of course then the question is, would this be a stochastic process that is wide sense stationary? And to be able to tell, we start by looking at the assumptions here. Is the mean constant and finite? And the way to compute that is you just take the expected value of the process, and I will then separate them in like this. So because they are independent of each other, notice that of course I will have a probability density function that contains the joint density of A and theta, but since they are independent, they will separate into A and theta, so I can divide the expectations this way. If I just call the mean here for MA for simplicity, I can move it outside of the integral, and I get the integral over all possible thetas. And of course, since we had the assumption here that it was uniformly distributed over 0 to 2 pi, that means that the probability density function will look like this. It's going to be 1 over 2 pi, 0 to 2 pi. So I will stop the integral at 2 pi into 0, and then of course it will take the value 2 pi, 1 over 2 pi in that range. So you will see that the integral turns to 0. So we are satisfying condition 1, and of course then we will have to move over to conditions 2 and 3 and see if we were also able to satisfy those. If I were to generate many realizations like I'm doing here, you can see that I have all possible amplitudes for a given time point. So at a given time point here, t, you can see that I have all the amplitudes. So if I would average over all possible realizations, the mean would be 0. And this would be true also here. So by just doing the simulations, I can see that this is indeed the case. So what about the covariance then? Well, I'll start out by computing the cross covariance between the process at time s and time t. Of course, I will just set up the expected value of the two as following the definitions, knowing that the mean is 0, so I can just remove those. I will separate out the expectations as before, and now I get the integral over the sum of the two cosines. And if I go through the process, you can see that the result will only depend on the difference in time s minus t. So we are satisfying condition number 2. If I let t be equal to s, meaning that I will have the variance of the process, this will turn into 1, and I will get something here that is finite. So I am satisfying condition 3 as well. So this is a wide sense stationary process. One thing that is worth noticing here is that the covariance function of a sinusoid is in itself a sinusoid. This frequency here of the autocovariance function is the same as the frequency of the sinusoid we had. This means that if, for instance, if I want to estimate this frequency, I could estimate the autocovariance function of the process, which is going to be a lot less noisy because the noise will not affect it when I am at lag higher than 0. And then I will estimate the frequency from the covariance sequence instead of looking at the process, which of course then will be affected by any form of noise. So the autocovariance function of a stochastic process which is wide sense stationary will only depend on the difference between t and s. So typically what we do is we write it as t and t minus k, and then we will just replace the notation. So we just say k here, that as the lag, the time difference between the two. You will see that many forms of books will use time t plus k and time t minus k, and this is just an unfortunate notational confusion in the literature that both of those are occurring equally frequently. I have chosen the t minus k here because that is my personal preference. It will only affect the notation in the following. So you'll get conjugates floating about and minus and plus signs. So you will have to stick with one notation, but it really doesn't matter. So, but you should be aware that you will see both forms of notation in the literature, and there's nothing wrong or right with either of the two. The autocovariance function of a wide sense stationary process will satisfy the conditions that it's going to be conjugate symmetric, meaning that if I look at the sequence, it will have the same structure on both sides, except then, of course, we'll have the conjugate. The variance is always going to be non-negative, meaning that the point that I have here at R0 is always going to be greater than or equal to 0, and it's also take the largest value, so there will be no other values that is going to be this large. There might be that you come up to this point again, but that will be for the case when I have a periodic process, but this will always be values that are less than or equal to the value at r of 0. Returning to our sinusoidal process, we can see that if I write it as t minus k, I will get this form as the autocovariance function, which is going to be a symmetric function with its maximum at 0, so that will satisfy condition 1 and 3 as we expect. And it also takes the largest value at 0, so condition 2 is also satisfied. As before, we are often interested in using the scale notation instead, and we will typically in this course use the autocorrelation function, much more than the autocovariance function, the ACF. The autocorrelation function is just the autocovariance but normalized by the variance, meaning that I will get a value between -1 and 1. Similarly, I can define the cross correlation between stochastic processes xt and yt like this. This will capture how much one stochastic process depend on each other. Say, for instance, that I'm modeling stock quotes. Then this would be the stock quote of, say, Ericsson and Google, and then I would like to know how much they two processes depend on each other. Then this would capture that, the cross correlation function. So this is going to be quite important for us to be able to determine how much do processes depend on each other. The cross covariance will be bounded by -1 to 1. To see this, just follow through these steps. Let's look at an example. Say that I have a mother here which has a heartbeat, and then this mother has a fetus in her stomach, and this baby also, of course, also have a heart, but which is much smaller. And I would like to tell whether the baby is alive or not by measuring the heartbeat here, by putting a microphone or a sensor in some sense here on the stomach. To determine whether the mother is alive, you can probably just ask her, so that is a lot easier than determining the baby. But if you look at the baby's heartbeat, what will happen here is, of course, you will get the mother's heartbeat, which is going to be much stronger, is going to affect your signal. This is going to be a very strong sinusoidal, if we make it simplistic, as a rhythmic pulse from the mother. There will also be the baby's heartbeat, which is going to be much weaker, and it will also have a higher frequency. That will be this signal. So if I would add the two, I would get something that looks like this, right? So I will have the stochastic process described as a sum of two sinusoidal processes with different amplitudes and different frequencies. And what I'm typically interested in is the frequency of the fetus heartbeat. If I look at the autocovariance function for this, these two will separate. So of course I will get an ACF, an autocovariance function, which depends on the two different frequencies here. So if I knew, say, the mother's heartbeats, I can, by probably just estimating the pulse, by measuring by her arm or something, I would be able to estimate the fetus heartbeat by just looking at the part that I haven't described. So this is, of course, not going to happen in reality. It's not going to be this easy because, as you know, anytime you measure something, there will be some form of noise. So if realistically, the process that I'm drawing here, it's not going to look like that. It's going to be, they're also going to be some kind of noise added to this measurement, say like this, meaning that what I will get is something that looks something like this. Now this is what I measure, and of course here I would like now to estimate the frequencies, but as you can see it's going to be very noisy because of this. So I need some way to describe this noise that I'm expecting to be able to see here. And to do that we introduce the notion of a white noise. A white noise is such that it's depending only at time 0. So if I would draw the autocovariance function for it, it will look like this. So meaning that it takes the value 0 at all lags except at the 0th lag where it takes the variance of the process. This is a white noise, and it's, of course, if you look at it, this is not going to happen in reality. You will not have any kind of noise that has these properties, that it will be completely independent from one time instant to each other. But it's a very useful mathematical model, and we will use it a lot. And it's also fairly realistic in some cases that you can approximate it reasonably well. It's also a reasonable approximation, for instance, for thermal noise, which has a very broad structure to it, and it's almost independent. So it's a reasonable model for us. If I would return to the fetus data, that means that I would add the noise to my measurement here. And if you look at the autocorrelation function, then there will be the autocorrelation function of the two sinusoids, which was what I expected, but I will also get the autocovariance of the noise. But as you know, this is going to have this particular property that it takes only values at lag 0. So I will then add something we call the Kronecker delta, which is just 1 at lag 0 and 0 otherwise. So it's just a complicated way of saying what I had in this figure up here. Then you can see that if I look at the autocovariance function of R of Y, the actual measurement, which consists both of the two sinusoid and also the additive noise, you can see that if I look at lags greater than or equal to 1, this part will not affect my measurement at all. So I should be able to estimate the fetus heartbeat by just looking at the autocorrelation function of the result and knowing the mother's heartbeat and ignoring the first lag in this sense, so that I'm not affected by the additive noise, getting something that consists, so that is a two sinusoidal problem that I wish to estimate, and then I can separate them two mathematically, of course. As noted, this is of course a simplistic model to have, calling it a white noise. Typically you would have something that is what we call a colored noise, when you have some kind of structure in it in your data, so that the samples that are close to each other will have some dependence to each other. We then say that it's a colored noise. But by estimating the color of this noise, meaning the structure of the covariance function for the low lags, we can compensate for that, and we will do that later on when we discuss the estimation part.